Hey everybody, continuing chapter 4, which is cycloalkanes. This was some of the last stuff we talked about, the ring strain of cycloalkanes, and how, of course, cyclopropane versus cyclobutane were pretty strained due to the small bond angles, right? There's a lot of bond angle strain here. And we'll show the structures of those in a bit. Cyclopentane was not as bad. This is not as bad there. And that was due to, in this kind of planar sort of conformation, it's about 104 degrees. Remember, sp3 geometry is 109.5. So what we did last time is we showed, at the end of the lecture, we were kind of quantifying the concept of ring strain using heat of combustion. What we did is we looked at a series of alkanes, in this case just like propane, butane, pentane, but you can do this over a long series of alkanes, and you burn or combust the molecules, right? And then what you do is you can look at the difference between in combustion energy, heat of combustion, versus like propane, butane, pentane, and the difference is all around 157 or so kilocalories per mole, right? And if you do this over a series of alkanes, maybe up to like 10 carbons, like longer, you get a number that's 157.4 is averaged. So it's basically what this tells you, this number, is that you have roughly 157.4 kilocalories per mole per CH2. Just the energy of just the each CH2. It says per CH2 down there. Okay. All right, and I emphasize that with this display, or this little item at the very end of the last lecture. All right, so we have this number. It's almost what we call a magic number. I don't think you're going to use this in a calculation, but we do need. You could call it a magic number, though. If you want to write the word magic number, write the word magic number. Magic number. All right, but it's not the kind of magic number or magic word that we would use in our potential quiz problems. All right, but anyway, that's an important number. It's the combustion, per CH2. The average combustion energy, right? 157.4. Okay, and given this number, we can say it's that our goal is to understand the strain of these cyclic alkanes, right? And these linear alkanes are a good model of a strain-free molecule. And right, if we have a series of linear alkanes like ethane or propane or butane, there's no strain in those in terms of like the structure, the way we have in like cyclopropane or cyclobutane. Those are strained, these are not strained. So linear alkanes are a good model of a strain-free molecule, okay? And we can use this to estimate the strain energy in cycloalkanes. What's the beeping? Whoops. Okay. Yeah, so we can use this to estimate the strain energy in cycloalkanes. All right. And let's do that. Let's estimate the strain energy in cycloalkanes. So you may need a new page in your notes for this part. What we're going to do is look at some different cycloalkanes. Let's write it to the left a bit more. Gotta have a lot of space for this part. So we're going to look at the cycloalkane. We're going to calculate the delta H combustion based on our magic number, right? It's 157.4. And so for what about like cyclopropane is how many carbons in cyclopropane? There's 3, right? 3 carbons. So what would our calculated combustion energy be? It would be 3 times negative 157.4. These are all kilocalories per mole. 3 times negative 157.4 equals negative 629.6. Okay? And then what we can do is we can compare that with observed. The actual experimental number. So the actual experimental number, oh my bad on the number, it's 3 times 157.4, of course that would not make sense, let's fix it. It's negative 472.2. Okay, negative 472.2. So the observed number is negative 499.8. And that's actually quite a bit more energy than we observed. So what's cool is that this will give us the amount of, this will calculate the amount of strain per CH2 in a molecule like cyclopropane. So what we do then is we say extra strain. Extra strain is basically the difference of that minus that, and it's 27.6 kilocalories per mole. Okay, and then the only other question is how much extra strain is there, not per molecule but per CH2. Per CH2. So we take this and divide by 3 and we get 9.2. So that's extra strain per CH2 for cyclopropane. That's actually, you'll see it's a fairly large number for these molecules. All right, now let's try cyclobutane. How do we calculate the amount of strain in cyclobutane? It's 4 times that number. 4 times the magic number is negative 629.6. Four times the magic number is 629.6, and the observed is 655.9 negative. Okay. So the observed, the experimental value is 655.9. Okay, and so you can see it's also more energy than we would calculate. And this is based on the magic number, which is like a strain-free molecule. So we can see there's definitely more energy produced, so you can say, well, cyclobutane has a little bit of strain in it. So we take the difference, and it's 26.3. Divide by the number of carbons, so there's 4 now. Take that, divide by 4, and you get 6.6. So you can see that there's a little less energy per CH2 in cyclobutane versus cyclopropane. Okay. Now we do like 5 carbons. Cyclopentane, right? Cyclopentane is 5 carbons, and this is 5 times the magic number. 5 times the magic number. 5 times the magic number. Those are like quotes. It's like we're repeating it. So 5 times the magic number would give us negative 787. The magic number again is 157.4, negative 157.4. Alright, and we get the experimental, and now it's negative 793.5. And take the difference, and it's 6.5. Divide by 5, and it's 1.3. So you can pretty clearly see that there's not as much strain in cyclopentane, right? Yeah. Per CH2, there's definitely less than like cyclopropane and cyclobutane. Now let's try cyclohexane. So 6 carbons, cyclohexane is 6 times the magic number. Gives us negative 944.4. Negative 944.4. Get the experimental. It's negative 944.5. So you can see those numbers are basically the same, right? So what do you think? Is this a strained molecule or not a strained molecule? Well, it looks like it pretty much matches, the combustion matches the strain of a strain-free molecule, because this column is a strain-free molecule, right? So we take the difference, and it's 0.1. Take 0.1 divided by 6, and it's basically 0.0. It's a very small number. What do you say? It's a strain-free molecule. Now the funny thing is you can't see why it's strain-free right now, because this hexagon shape is not the real structure of it. We'll see the real conformation in a bit. It's called a ch4 cyclohexane. So ch4 cyclohexane will be a representation of cyclohexane that shows it being strain-free. Okay. What about 7? What's the name of that molecule? I wrote 7 in there, but and you know, like, how do you draw that? You may have never drawn that before. I call it a truncated stop sign. So it looks like a stop sign, but we have a line on the bottom. And if it was a stop sign, it would be a line on the top also, right? Like a octagon. And anyway, what's this name of this is called cycloheptane. Right? Cycloheptane. Of course, that's cyclohexane and cyclopentane and cyclobutane and cyclopropane, right? Anyway, let's just do the calculation for cycloheptane, like a slightly larger ring. So it's 7 times the magic number. 7 times the magic number is negative 1101.8. The observed is negative 1108.2. Okay, and yeah, so there is actually a little bit of strain. You can see that number is a little more negative. The experimental heat of combustion is a little more negative than the calculated, right? So take the difference, and it's 6.4. And then we can determine per CH2. Per CH2, divide this by 7, and you get 0.9. And so what you can see here is it looks like there's kind of a magic, like an optimal ring size, right? 6-member rings give you no strain at all. If it's either smaller ring or larger ring, you start getting strain. So I'll explain why all of these have strain to begin with in a second. And also, as you go further, like if you do 8, that's cyclooctane, right? Cyclooctane. And as you go further down, you get additional strain. So I'm not going to do that calculation. I'm just going to say etc. And I think it's table 4.2 in the book. So you can see more calculations of this if you're interested in it. But the big takeaway here is cyclohexane is strain-free. We've calculated cyclohexane to be strain-free. Okay. Okay, so what that showed us again, very cool. We can we're able to quantify the strain in a couple molecules. Able to quantify strain in, you know, we looked at cyclopropane, cyclobutane, cyclopentane. The big weird, other weird one is cycloheptane, which is 7, right? That also has strain. But what we also determined that we showed that cyclohexane is strain-free. That was kind of like a conclusion. Cyclohexane is strain-free. Okay, and then the larger rings have strain also, like 7, and also we'll just show 8 as an example. What kind of strain might this have in it? And I'm gonna give a name for this right now, and we'll talk about it later. But if this carbon, we'll just consider these 2 carbons, right? If you build a model of cyclooctane, those carbons are actually talking to each other. Like, when I say talking to each other, I mean they're bumping into each other. So this, with a kind of large molecule like cyclooctane, the CH2s are actually bumping into each other. Okay, and maybe I will. I'll try to build a model that sort of shows that. I'll give you a name for it. I'll give you a name for it right now. It's called transannular strain. Transannular strain. What do you think that means? Transannular strain. If you've never heard the word annular before, which you probably have not, annular means a ring. I think it might be a Latin type thing. And what we mean is that these CH2s are kind of bumping into each other, and that creates a little bit of strain, and that's what we call transannular strain. Okay? So that's like cyclooctane. Also, like cycloheptane. Have that kind of transannular strain. Okay? So I just, for fun, got my models out to build a couple of these rings. And if you have your models, I would try to do this too. It's not that difficult. I want to show cyclooctane. So this is the 8-member ring, right? How many carbons in cyclooctane? Should be 8, right? And what you can see is in this kind of large ring that the carbons across the ring can kind of bump into each other, right? So there's like the CH2s across the ring are kind of bumping into each other, and that is what we call, what is it? Something annular. So that's what we call transannular strain. So there's a little bit of unhappiness due to these CH2s kind of bumping into each other. Okay, so that's 8-member. I'll quickly show 6 real quick while I got them out. So you can do this with your own models also. Just, you know, attach the carbons up and put 8 carbons in a ring, and you'll see you can experience transannular strain, right? Okay, so then I take out 2, and now I'm left with 6. What we're going to see, and this is a preview because we're going to do a lot with this, 6-member rings have something called a chair form. And this is, you can see all of the CH2s are totally happy tetrahedral, and there's no strain at all. So this is what we're going to call, this is cyclohexane in this thing called chair cyclohexane, okay? All right, and so we'll talk a ton about this, but you can see it visually. We'll do this later. Yeah, okay. There's kind of like 2 forms. I'll mention it now. You're going to see it later. But the 2 forms can interconvert. It's called flipping. So here's the chair form of cyclohexane. You could build this with your own models. And basically, the flipping is I'm going to take one side, like this side. I'm going to flip it down and flip the other side up, and there's a little bit of an energy barrier. Aha! That's called it flipping. So cyclohexanes do this thing called flipping, and I'll talk about it, and you know, you'll see this in a little bit later too. All right. So I can take my cyclohexane and I'll flip it the other way. They go back and forth, flip, flip, and now I'm back to the other one. That's called flipping, and the chair forms of cyclohexane flip. Okay, so you'll see that. What about five carbon? Let's do that. Cyclopentane. There's a little bit of energy in there, and here it is. There's cyclopentane, five carbons. It's a little puckered. It's a little bit puckered. Like one side's usually a little bit higher. You know, we'll talk about that. It's a little bit puckered. This is not perfectly happy. And you might remember from ethane chapter 2, the end of chapter 2, we did Newman projections. Remember that? Newman projections. There was a kind of strain energy when things were eclipsed, right? And these are actually eclipsed. So this CH2, front CH2 and the back CH2 are eclipsed, right? And what is that called? What was it the weird eclipsing interaction called? It began with T. It was in chapter 2, T. When like ethane, think of ethane, CH3, right? We did Newman projections and we showed two conformations. One was staggered, one was eclipsed. The eclipsed kind of looks like this, right? And we gave it a name of the strain, right? It's called torsional strain. So this is torsional strain, and this kind of will explain why cyclopentane is a little bit unhappy. Just a little bit. It's not as bad as cyclopropane and cyclobutane. Just a little bit unhappy due to this torsional strain, which is eclipsing, right? What's the opposite of eclipsing? Eclipsed is staggered. Think about ethane again, which we saw before. That is staggered ethane. This is eclipsed ethane, right? So we remember that staggered is a little bit happier than eclipsed. And what's the kind of strain with eclipsed ethane? It's called torsional strain. So yeah, there's a little bit of this torsional strain going on in ethane or propane or even, you know, butane with the different eclipsed interactions in butane. Remember butane, it's 4 carbons. Okay, and we see that same kind of thing. Whoops, microphone. We see the same kind of thing going on in cyclopentane, right? So like these 2 carbons are eclipsed and there's a little bit of torsional strain. Okay, all right. So do you think you can make model of cyclopropane or butane, 4 carbons? The answer is no. You'll break your models. They're very, very, very strained. Your models are too fragile, so don't try it unless you want to break your models. Cyclopropane and cyclobutane, which are 3 carbons and 4 carbons, are very, very, very strained, and due to the bond angles, just not happy at all. So can't make models of those. They have computer models and you know, YouTube or various internet resources, but don't try to do it with your own models. All right, so back to the little video camera mode. What we just saw was, well, we visualized cyclooctane having transannular strain. The case is also for cycloheptane, 7 carbons. So 7 or 8 or above, you get this transannular strain issue. All right, we saw that cyclohexane is strain-free. Everything's nice and tetrahedral. It's actually all staggered also. I didn't say that in my video just now, but everything's staggered in chair cyclohexane. Chair. All right, chair cyclohexane. All right, and then let's just get rid of this. 7 is kind of in the larger category, larger rings category. But we saw the cyclopentane was relatively strain-free, but it had a little bit of eclipsing interactions, right? CH2s next door to each other were eclipsed. What's the name of that? When CH2s are eclipsed, it's called torsional strain. So cyclopentane has a little bit of torsional strain. And then these guys are just extremely strained due to the bond angle strain. we'll also see that they have torsional strain as well. All right. Okay. So, okay, so let's talk about number 3 now, which is the strain and cyclopropane. The strain and cyclopropane. The little triangle thing. So what was the number per CH2? If you look back in our table, it's a pretty big number, and it's 9.2 kilocalories per mole per CH2. So it's a fairly, of all the ones we saw, that's the biggest energy per CH2. Alright, so the way it kind of looks, I mean, you got your 3 CH2s that are bound in a ring, right? And why is it strained so much? Why strained so much? Why is it so strained? And there's two reasons actually. One is the bond angles, right? That's a huge problem. The molecule is incredibly unhappy due to the bond angle strain. What was the bond angle strain? It's roughly 60 degrees between the CC bonds are roughly 60 degrees to make that really small ring size. There's also another problem, which is indeed it has the eclipsing CH interactions. And that's called, what's the name of it? When things are eclipsed, it begins with T, torsional strain. Now what does torsional strain really mean? And we talked about it when we introduced it when we talked about ethane, right? Ethane, CH3CH3, that little bit of interaction between the neighboring CHs when they're eclipsed, it's called torsional strain. So what is the unhappiness? The unhappiness in torsional strain is due to the neighboring CH electron clouds bumping into each other. Neighboring CH electron clouds bumping into each other. Neighboring CH electron clouds bumping into each other. Okay? And so it's not the CH atoms, it's not really the atoms, it's more the electron clouds. That's the way I've always understood this. Okay? That's the way most books explain it also. It's really the electron clouds. It's not like the CHs are bumping into each other, it's really the electron clouds that are bumping into each other. Okay? Alright, so when you think about cyclopropane, how do you think the orbitals are arranged? Because what is the hybridization of these guys? Each of them is a CH2, right? So there's 4 things on the carbon, right? It should be sp3. It should be sp3, right? And the bond angle is normally 109.5. So cyclopropane does some really weird bending to make this happen. Because it's supposed to be 109.5 if it's sp3, but if you look at the molecule where the atoms are, it's really about 60. So how does, if you're supposed to be 109.5, how does it fit in how to accommodate 60-degree bond angles. So it does something weird. The CC bonds are bent. CC bonds are bent. How are they bent? So the bonding kind of looks like this. You have C, C, C. Draw your 3 carbons, right? You have your 3 carbons, and what happens is there's kind of like a, let's draw this a little better. Okay, there's one bond, and then we have another bond, and we have another bond. And each bond's got 2 electrons, right? And then we got our H's. H and H. H and H. H and H. Alright? Cool. So, yeah. Oh, sorry. Now you can see it. Okay. So yeah, that's the way it looks. Start by drawing your 3 carbons, and then you draw these kind of bent bonds where there's the orbitals overlap, and you have 2 electrons in each bond, right? And then you fill in your H's, right? Okay. So these are bent bonds, and some books call them banana bonds. I don't know. They if you Google that, you will, in like cyclopropane, you'll see pictures of bananas, and how these kind of look like bananas, I guess. But you know, it's really just a bent bond. Compared to normal bonds, that's weird, because a normal bond like ethane, right? Ethane does not have bent bonds. A nice happy molecule like ethane does not have this. Okay, so after you do this with the bent bonds, even though the CC C bond angle is 60 degrees, right? Based on, you know, if we had a straight line between the carbons, you'd have 60-degree bond angle. After you do this bending, the orbitals are nearly tetrahedral. Which is roughly 104 degrees or so. Or in this case, it's in this case it's 104 degrees, which is almost the same. Almost. What's the normal one for carbon? 109.5, right? Okay. So yeah, it's almost there, and the way they accommodate that is by using these bent bonds. All right. They have a nice figure in the book. Figure 4-2, I think it's B. I think that's what it is. Check that, and you can actually see like a computer model of how this looks with its bent bonds. But this is a pretty reasonable depiction of what the bonds and the orbitals look like. All right, and the bonds are bent. And is that happy? Is it happy to have orbitals bent like this? No, it's not. That's why there's all that strain energy. This is a really unhappy way to accommodate the 3-carbon cyclopropane structure. Okay, that's why this is so unstable, and you get that big strain energy. All right. Interestingly, with the unstable structure in cyclopropane, it can be cleaved. So there's a chemical reaction that'll actually cleave cyclopropane very easily, because all these CC bonds are weak. They're unstable bonds. So it's very easy to react this with H2 and palladium on carbon. H2 and palladium on carbon. And what does that mean? Palladium on carbon. We're going to learn a lot about that later, but it's palladium, the metal, carbon is just basically charcoal. And then you're using H2, hydrogen gas. And what we're going to do is find that you can cleave cyclopropane to make propane, right? What's the molecular formula of cyclopropane? It's all cyclic molecules. It's like C3H6, right? C3H6. What's the molecular formula of propane? It's C3H, remember it's H2X plus 2. So it's CXH2X plus 2. So it's H 3 times 2, 6 plus 2 is 8. H8. So you're going from C3H6 to C3H8. Obviously you're adding 2 H's. And so we're adding H's, right? I'm going to show a simplistic mechanism. Simplistic. Okay, we can give a more realistic mechanism later, but I just want to show, you know, how does H2 get incorporated in here in a way we can just kind of draw it. Well, let's draw a simplistic mechanism. So let's draw cyclopropane. Okay, and you can imagine like we have H2, right? H2. And so what we could do to sort of show this, how these would interact, I'm going to use a dotted color, dotted blue, alright, between the carbon and the H, the carbon and the H. And then I could really just do this. So one H goes to one carbon, the other H goes to the other carbon, and the bond gets cleaved. What does that make? If the bond gets cleaved and then one carbon gets one H, the other carbon gets the other H, it looks like you get HH and then you get another HHH, right? Of course that's the same as propane, the product. Okay, so yeah, this is simplistic in that it doesn't account for what the palladium's doing. And palladium, we're going to talk a lot about palladium later, so let's not worry about what it's doing in this situation. But this is a little unrealistic due to the we're not accounting for the palladium. Anyway, yes, a very unstable molecule like cyclopropane gets cleaved in the presence of H2 and palladium on carbon to give you propane. The bond is very easy to cleave. Okay, I'm going to say this is abnormal right now, that you can cleave a bond, cleave a CC bond. A normal CC bond cleaving with H2 is very abnormal. You can only do it in this case because the bonds are so weak. Abnormal. Okay. Alright, so we talked about cyclopropane and kind of the strain energy in cyclopropane. Let's talk now about number 4, which is strain of cyclobutane. How much strain was in cyclobutane, which is the little 4 carbon thing? It was 6.6 kilocalories per mole per CH2. So not as bad as cyclopropane, but it's definitely a unhappy molecule. And so how does it the structure change to accommodate this strain. This adopts a puckered conformation. Okay, I'm going to draw it. You don't have to reproduce this. It's also in the book, so you can just see what it looks like, but I'm not going to ask you to draw this. Much of what we're going to care about in Chapter 4 is going to be related to cyclohexane. You should know about the basic, properties of these other ones, and the, what type of strain you have. But when I draw like a puckered conformation of cyclobutane, that's not something that you would really need to draw. So what do I mean by a puckered conformation? I'm going to draw it kind of like this. Okay, so it's not a square. That's the thing is you look at that, you're like, oh, it's a square, right? Well, it changes its structure to try to relax the bond angle strain, and so you get CH2, CH2, and then like here you have an H going here and an H going there, and then this one there's an H going up, an H going down, and then you get an H going here and an H going there. So it's kind of like this bent sort of shape of cyclobutane, and it rapidly flips to an alternate conformation, which kind of looks more like the opposite, right? 4 carbons, and H, 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 H. All the H's are trying to be as far apart as possible. And these go back and forth. This is kind of a poor drawing. This dots should maybe be a little lower, but let's not worry about this. Just understand there's 2 conformations, and there are these puckered conformations. Alright? Alright, so why is it puckered? Why puckered? Why does it do that? It relieves some CH torsional strain. It relieves some CH torsional strain. And again, the torsional strain is due to eclipsing interactions. The eclipsing interactions are the neighboring CH2s that are kind of eclipsed, right? And that's a electron cloud interaction. Okay. In the end, the CC bond angle is roughly 88 degrees versus, what is it in a totally happy tetrahedral structure? 109.5. So is that happy or not? No, it's not. And it's just another one of these kind of unstable small ring sizes. Okay. The bonds are bent slightly also. Kind of the way cyclopropane does it. There's a little bit of a bent bonding thing going on. The structure is a little more complicated though for cyclobutane versus cyclopropane, because we have equilibrium between 2 conformations, right? Okay. And it can also be cleaved. Cyclobutane can also be cleaved. It can also be cleaved this sort of similar manner that cyclopropane could be cleaved. H2 palladium on carbon. Okay, So the 4-carbon cyclobutane can be cleaved with H2 palladium on carbon because it has such unstable, sort of unusual bonds. And it's something kind of the same way. I'll just draw it over here underneath. We have H2. I'll just draw it kind of, you can get the idea. So we have 4 CH2s, right? CH2, 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 CH2. And H2 just kind of sneaks in there. And then the bond cleaves where kind of the same exact way that we did it for cyclopropane, right? Where one H goes to one carbon, another H goes to the other carbon. You have a net introduction of 2 H's, right? And it goes from C4H8 to C4H10, right? Because you added 2 H's. And the CC bond gets cleaved in this process, right? And like I said before, this is a very abnormal reaction that occurs for really small rings, like basically cyclopropane and cyclobutane. It's not going to happen on cyclopentane. It's not going to happen on cyclohexane. It's not going to happen on cycloheptane or octane, or even the large rings don't do this. It's really just the tiny ones that have very, very strange bonding, like cyclobutane and cyclopropane. All right. Okay, so yes, cyclobutane can be cleaved by the same manner. Cyclobutane can be converted to butane. All right. All right, so we did cyclopropane and cyclobutane. They're really highly strained ones. Let's do cyclopentane now. Cyclopentane is not as strained. If you remember the number from our little table, it's 1.3 kilocalories per mole per CH2, which is definitely not as bad as cyclopropane or cyclobutane, but there's some strain there. The CC bond angle is about 108 degrees, which is not that bad. Which is not that bad considering the hybridization of cyclopentane. All of the CH2s are sp3 tetrahedral, so you know it's close to a perfect tetrahedral 109.5. Okay, yeah, degrees. So not that bad. But why is there any strain at all? Why is there strain? And the answer is there's a little bit of this torsional strain. CH torsional strain. CH torsional strain. And so that's going to be neighboring CH2s. Neighboring CH2s. And the electron clouds. And they have to, in order to be torsional strain, what kind of interaction is it? It's eclipsing, right? Alright, so we'll see these eclipsing interactions. Easiest way to draw this, it also has two main conformations. Two main conformations, which I call, whoops, sorry. Let's try to draw this again. Okay, the two main conformations are kind of look like that. And these are called envelope conformations. I like to call them space shuttle conformations because it kind of looks like a space shuttle. But anyway, they basically alternate, or they flip and they go back like this. They're basically two envelope conformations, and you can see what where the eclipsing interactions occur, because like these CH2s are basically eclipsed, right? If you would kind of like look down the CC bond, you'd see the neighboring CH2s are eclipsed, and by flipping between two conformations, it can kind of get rid of some of the eclipsing interactions. So this is what the molecule does. All right. There's also, in the book, there's two other ones. They call them half chairs. Half chair conformations. I'm going to ignore those. It's not really that big of a deal. So you're not going to be tested on them or quizzed on them or anything. Yeah, but you can see them in the book. There's a couple different conformations of cyclopentane, but these envelope ones are the dominant ones, right? What did we say about, you know, which of the bonds are prone to cleavage with H2 palladium? So we do H2 palladium on carbon. Which ones did we say were prone to this reaction? We said cyclopropane and cyclobutane. This is a relatively stable molecule, so it does not do this. It does not cleave from cyclopentane to pentane, and so another way we say that is NR. No reaction. Doesn't happen. Not strained enough, right? This is not a strained enough molecule for this CC bond cleavage reaction to occur. Alright. So now we're on to cyclohexane. And what do we say about cyclohexane? Is it a strained molecule or a non-strained molecule? Cyclohexane is strain-free. Okay, so by saying that, you know, all of the carbons are nice and tetrahedral, no bond angle strain, and everything's staggered. It's not eclipsed. So all that eclipsing interaction stuff is gone. And so you can draw a kind of naive representation of cyclohexane that we already told you what it really looks like. It has a word, right? It's what you're sitting on right now, a chair, right? I'll show the chair form in a second, but let's show a kind of naive representation of cyclohexane first, because you might think it just looks like a hexagon, right? You might think it just looks like a hexagon that kind of looks like this. Right? Cyclohexane. If it did sit like this, and it was planar, like all the carbons are in the same plane, the bond angle would be 120 degrees, which is actually not that bad. But the big problem is what? If it had like a planar conformation, like all the carbons are in the plane, right, in the page, then what would happen to each of the CH2s? They would all be eclipsing, right? One H would be coming towards us, one would be going away. One H would be coming towards us, one would be going away. And they would be all eclipsing, and that would be very problematic. All CH2s would be eclipsed, right? So what does it do to avoid that problem? And the way it avoids it is it adopts the chair conformation. So adopts chair conformation. Okay, now we have to draw the chair conformation, and this is one of those things that Organic 1 students struggle with. So we're gonna practice this about 1,000 times. How to draw the chair conformation, and you will be required to do this on quizzes. And it's going to be a major focus of this chapter and the quizzes and stuff. So I am going to. I'll draw it the first time right now. All right. Okay. So a way to draw the chair conformation is like this. So follow what I'm doing, and we'll practice it more in some of the other videos. Okay, so what we're going to do is draw two kind of lines and make them parallel. Okay, so they're parallel, and roughly the top should be at the same point, right? Okay. Okay, so I'm trying to make, you know, it's not like one's higher than the other. They're both parallel and they go kind of to the same point. Now I'm going to draw these guys. This bottom right, I'm going to go kind of towards the direction of the other carbon, and then this one's going to kind of go down in the direction of that carbon, right? Okay. And now what I'm going to do, I'm going to go to the bottom right one. Now I'm going to connect this one to that carbon. So I'm going to go like this. Okay. And now I'm going to do this one also to this carbon. But the big thing is that these lines, the lines I'm drawing now, should be parallel. So notice how this is parallel to this. It's the same angle. This is parallel to that. It's the same angle. Well, the new line needs to be parallel to this one. And right now it might not be. So I'm going to maybe go a little further. Maybe that'll work. Yeah. Now as I go up, it's going to be parallel. So that's a perfect, I think that's that's a perfect rendition of chair cyclohexane. All right, 6 carbons, right? Okay. This is a chair conformation of cyclohexane. Where do the H's go? All right, so this is going to be another struggle. So the first, I'll go maybe from the top right. So they're going to alternate. You're going to have H's go straight up and straight down. So it's going to be like straight up, straight down, straight up, straight down, straight up, straight down. All right, let's draw those first. So this one is going to be straight up. This one's going to be straight down. This one's going to be straight up. This is going to be straight down. This is going to be straight up. This is going to be straight down. So that's how many? 1, 2, 3, 4, 5, 6. Okay? We have 6 more. I'm going to give these a name real quickly. The ones that go straight up and straight down are going to be called axial. All of them, all the straight up, straight downs are axial. They go up and down, like in an axis, or I don't know. Axial in this manner refers to straight up, straight down. Okay, so then these are maybe the easy ones, right? Now let's draw the other ones. And there's going to be a trick to it, because for every axial one, there's going to be another one called an equatorial one. All right. If on this carbon we have a straight up H, we're also going to have equatorial, which is going to go down. So this is up, and the one's going to go down. And this is the angle is, you have to be very careful. Okay, so what it's going to be is like this. It's going to be going kind of down like this. That's my equatorial one. I'll write the word equatorial. Equatorial is kind of going down to the right, all right? Okay. Notice something about this equatorial of CH. Notice how, what is it parallel to? Or like the same angle as? It's like this CH is the same angle as one carbon, one bond over. So like this. You notice how this and this are roughly the same. They should be identical, and I did my best to make it identical. See how this angle and this angle and this angle are all the same? Angle, 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 all the same? You need to do that for every one of your equatorial hydrogens. Okay? Every equatorial hydrogen is going to be parallel to one bond over. Parallel to one bond over. What about this one? All right? Where is it going to... First of all, if there's an axial going down, where's the equatorial going to be? Is it going down also, or it should be going up? The answer is it's going to go up. Because if you have something axial up, you have equatorial going down. Axial down, equatorial is going to go up, and it's going to be parallel to one bond over. So this is the bond it's going to be parallel to, or the same angle, right? Angle, angle, and now my equatorial is going to go parallel to one bond over, and it is up. See what I did? See how that CH was parallel to this and this? Well, this CH is parallel to this and this, parallel to one bond over. So there we go. These two are going to be trouble, so let's wait on them, because they're a little hard to see. Let's jump to the other side, though. Okay, so we have an axial going down, straight down. Where is the equatorial going to be? It's going to be going away from the ring. They always go away from the ring, and it's parallel to one bond over. So it's going to be parallel to this bond and this bond, and it's going to be in the same angle. This is going down, this is going to go up. See it? Okay, this one, all right, we have an axial up. Where's the equatorial going to go? Down, right? Axial up, equatorial down, and so it's parallel to one bond over. The H is going to be parallel to these two bonds. And so I'm going to go like this. Very cool, very cool. We're almost there with this. All right, what's missing? These two guys. These are the ones that students have difficulty with, I think. Those are not that bad. These might be weird. Okay, but it's the same rule. The H, the equatorial H, well, we have an axial H here, and there's an equatorial H. It's going to be parallel to one bond over. They always extend away from the ring. So it's actually going to be like these two guys. And it's just going to be coming this way. So it's like this, H. There we go. Very cool. So it's coming towards us, right? Okay. What about this one? Now it's in the back. This is further in the back, and the H is going down. The axial H is going down. Where's the equatorial H going? Parallel to one bond over and away, so it goes kind of in the back. Okay. H. That is our first successfully drawn cyclohexane. Okay, you're going to practice this 1,000 times. 1,000 times, not one under 1,000. You're going to do this literally 1,000 times. All right. Where we draw all the axials and all the equatorials. So we'll practice this a bunch, okay? What else am I going to say real quickly about this? Don't use wedges or dashes. Do not use dashes and wedges. Remember those things? Like this. Or, you know, in general, when you're drawing a chair cyclohexane, we need to visualize the three-dimensionality of it just by the way we draw this. We don't use dashes and wedges ever, 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 ever for cyclohexanes like this. All right. So when we draw chair cyclohexanes, all of the three-dimensionality is drawn in the ring. These are not. There's no dashes and wedges. These are, I just made the bonds a little bold-faced, but that's just the way I drew it. All right. Never use dashes and wedges. So some students are going to be doing this on the quizzes or whatever of like, well, I'm just going to quickly draw it. You'll draw something like this, and they might start to do a wedge or a dash. That is wrong, 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 wrong. Never do that. Never, never, ever. You'll never have a reason to draw dashes and wedges on a cyclohexane like this. You just use the up and down axials and up and down and up equatorials, and that shows the three-dimensionality of it all. Okay. Another thing, just looking at our chair cyclohexane, a couple of little quick points. All bond angles are very close to 109.5. So they're perfect tetrahedra. There are no eclipsing interactions. There's no eclipsing interactions. So what are they if they're not eclipsing? When we consider each of these CH2s, are they, if they're not eclipsing, what are they? What's the opposite of eclipsing? They're staggered. All are staggered. All are staggered. And we can see this with the Newman projection. So let's draw a quick Newman projection of cyclohexane. Remember, what's Newman projection? The Newman projection was how we envisioned or visualized eclipsing and staggered interactions, like for ethane, propane, butane, and stuff. Remember those in Chapter 2. Chapter 2. Chapter 2 is where we learned about Newman projections. Newman. It was the end of Chapter 2. And it easily shows eclipsing and staggered conformations. So I'll show it. I'll show the visualize with Newman to show that there's no eclipsing interactions at all. Remember, like in ethane, for example, this was an eclipsing interaction. Ethane eclipsed versus ethane staggered. And I think I misspelled staggered on the last slide, so it's SATAGG, staggered ethane. Okay? So staggered is generally the happy one, right? Well, let's draw cyclohexane with Newman projection. It's kind of scary because it's a big molecule, but it's not that bad. So if we look down two of the carbons, CH2, CH2, we basically get this kind of representation. Remember, what's the middle of the Newman? This is a carbon, right? We have a dot and a circle. The dot is the close carbon. The circle is the further carbon. Okay, so we got the two closer carbons, and we have two further carbons, and everything is staggered. It might be good to get your models out and build a model of cyclohexane. Okay, and then you can kind of look at it, and you can see these the two closer carbons and the two further carbons, and how everything is staggered all around. There's no eclipsing the way we saw ethane eclipsed, or you know, even like cyclopentane or whatever. This is a very stable strain-free molecule. Okay. We said that cyclohexane has axial and equatorial CHs, right? Cyclohexane has axial and equatorial CHs. The axials are straight up, straight down, up and down. Equatorials go off to the side, off to side, and parallel to one bond over. That's going to be a way to, like a guide for how you're going to draw these things. Okay. so the axials, wrapping up here pretty quickly. Axials alternate straight up and straight down. Straight up, straight down. Equatorial also do. But they're kind of off to the side, right? And of course there's always 6 axial and 6 equatorial. But on any carbon, one will be like up in axial, the other will be like down in equatorial or something. You'll never have like 2 things up at the same time, right? So, okay. We're going to try one more practice drawing, just in the last second. We'll just do it on the back here. All right, let's do one more time. One more practice drawing of a cyclohexane. All right, so what was the trick? I'm going to do it near the top of the page because I mean, what I'm trying to do is show you like when I draw like the left side and the right side, they're relatively at the same height. Okay, like on your page or whatever. Or if you have like ruled pages with little lines, I mean, they should be roughly at the same height. So it's not like one's higher or lower. They're roughly at the same height. Okay, maybe we'll make it a little longer. Okay. Okay. What was the next thing I did? I'm going to just connect from the bottom left towards the top right, and I'm just going to kind of go in that direction, and I'm going to go in that direction. All right. And then I'm going to go from the bottom right to this line, and there we go. Wonderful. There's our chair. Notice a couple things. That's parallel to that. That's parallel to that. That's parallel to that. Not perfectly, but pretty close. Okay. Now I'm going to do my axials. H, 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 H. Okay. My up, down, up, down, up, down. 6 axial H's. And then I'm going to do my equatorials, and they're always parallel to one bond over. So if I have a up and axial CH here, I'm going to have a down and equatorial CH on the same carbon. What bond's parallel to one bond over? That guy. That's the parallel bond. So kind of go down like that. Down and up and axial, down and equatorial. Down and axial, up and equatorial. I do the middle ones last because those are the ones you're going to probably screw up. So now we go to the far left, and I'm like, well, I'm down and axial, let's go up and equatorial, up and axial, down and equatorial. Now we'll go to like this one in the back. I have a down and axial, so where's the equatorial going to go? It's up and equatorial, back in the distance, and it's parallel to one bond over, which is this and this, and it's going to go kind of like that. Alright, and now this one is the closer one to us. It's up, got an up and axial, and it's got a down and equatorial. Okay? Now, what if a student did this? It would be wrong, right? It needs to be parallel to one bond over. This is not a tetrahedron now. So we have to, that's why you have to be careful about where you draw your equatorial ones. Actually, let's draw one more bad one, and I'll finish it. We're basically done. What about this? Well, now the H is going kind of into the ring. That's not right, right? Everything's extending away from the ring. So that's bad, too. Let's show the good one. It's going to be kind of coming towards us and parallel to one bond over, parallel to there and there, right? Okay. And also remember, no dashes and wedges. You don't draw dashes and wedges when you draw cyclohexane. Just do this, practice this a couple times, and we'll explain more later. Alright, we're done.